Up an announcement up on Canvas about quizzes, upcoming quizzes, and exam 2. I decided to give everybody a little bit more time and move it all to after spring break. Should give you enough time to hopefully study and catch up on everything that you might need to do. So we're going to take 2 quizzes when we come back. One on naming on Monday, one on basically bonding and like balancing equation, I think, in types of reactions, which is a little bit of 6 and a little bit of 7 as well on Wednesday. And we're going to move the exam to probably the week after that, which would be like the week of the 7th of April, I believe. So I think it will be probably on that Wednesday, which is the 9th or 10th, one of those days, whatever it is in that announcement. So if you didn't look at the announcement, make sure you do. It will explain basically all those things along the way. Any questions on that there? Okay. All right. So we were talking about something. Now, we were talking about equations here, and we were talking about balancing equations. Remember that when we have a chemical equation, we have reactants on the left-hand side of the arrow, and that's really your starting material. They go to products on the right-hand side of the arrow. Now, when we talked about it, we always want to make sure whenever you're using an equation, especially a little bit later on here in this chapter towards the end, definitely always important, pretty much in chemistry, that those equations are balanced. And you never really, in any situation, usually in chemistry, you want to use an equation that is not balanced. And remember that when we do balance an equation, put 2 there. Let's try that again. A is what I'm looking for there. We only, as we talked about, we only change the coefficients. And the idea there is, again, as we talked about, pretty much in a chemical reaction, all we're doing is breaking bonds and making bonds. That's all electron based, which means we don't do anything with the nucleus, and we never change elements. So however many elements you have on the reactant side, you should have the exact same number of those elements on the product side. Again, they just may be in different sort of compounds over there. And that's the idea of balancing it. So only coefficients. Again, we never, for example, if this was something, we never change the subscript as we talked about. Again, if you do that, you're actually changing what that thing is. So you never want to change that. You also never, as we also talked about, want to put any big numbers in between, like letters or anything like that in the symbol. So no big numbers like in between or anything of that nature. Again, as we talked about, kind of a little different ways to sort of balance it. So if you have a basic equation that really doesn't have polyatomic ions in it, I like to do the table method there, where you just kind of make a table of everything you got on the reactant and product side. And again, you start with kind of coefficients. As we did in a number of those examples, I would start with what seems easiest just to kind of fix. Something that's maybe just in one sort of formula on each side of the arrow is a good place to start. Then kind of leave things that are a little bit more complicated in the sense that we had a couple examples, I think, where we had oxygen in a couple of things, and then one side, it only was on one thing, or nitrogen was in a couple of things, and it was just in one place on the other side. So, those guys you kind of want to leave to the end to fix, and that usually works really well. Remember, as you go through the balancing process there, you'll probably fix one thing and mess up something else. So that's a very common thing that occurs as you go through it. But eventually everything should fall into place. Remember, though, if we do have some equations that involve polyatomic ions, a lot of times it's much easier to kind of keep those together and kind of balance them as like units rather than sort of individual ions, or sorry, individual elements. You could, if you wanted to do individual elements, but as we talked about, again, you'll have a lot more sort of multiplying in and numbers to kind of keep track of. So if you kind of keep those polyatomic ions together when you're balancing, that's a really good way to balance those pretty quickly. In that method, essentially, you start with whichever polyatomic ion you want to balance. You think of them as whole units, and you put numbers to balance a polyatomic ion. The key when you do that is, for example, if you had sodium nitrate and you wanted to balance the nitrate by putting a 2, you would then go to whatever it's attached to is the next place you go. Then you go fix the sodium on the other side, and whatever the sodium's attached to, then you would go fix that guy on the other side. And again, eventually, it will all sort of fall into place. Regardless of what you do, what method, whatever way you do it, when it's all said and done, all the coefficients need to be whole numbers and they do need to be the simplest set of whole numbers, as we talked about. So again, if you found a way to balance this equation and this thing was all balanced, we could still go through all these guys and really reduce everybody down by 2, which again would give us the properly balanced equation that looks something like that. And that's again what you should sort of end up with. We also saw that in certain cases, a fraction is maybe useful to use, and you absolutely could use a fraction to balance an equation. You just need to get rid of the fraction when it's all said and done. So that's sort of what you need to do. Remember, when you're trying to choose the fraction that you want to use, it's a pretty simple recipe. The number on top is the number you need. So whatever number you need to balance it goes up on top for the fraction. And usually the bottom should match the subscript that's there. So for example, if I use that one I had up here, something like that, that too should be what's on the bottom, whatever that subscript is. And that will always give you sort of the right fraction to use. And again, to clear the fraction, we need to multiply everybody in the equation, not just the fraction, but everybody in the equation by the denominator, the number on the bottom. And that should then give you a balanced equation that has all whole numbers, and it should still be balanced at that point. Any questions on balancing equations or anything like that? Oh, God. All right, now that we talked about balancing equations, we're going to talk about a little bit here ways to classify reactions or types of reactions that occur. There are, as we will talk about, really 2 big category of reactions. And under those kind of big category reactions, you could actually qualify or classify reactions in multiple ways. So what I mean by that is you could look at a reaction and there can actually be, for example, 3 different ways you could classify the same reaction, and they're all legitimate ways that you could actually classify them. So there are multiple ways you can actually classify a reaction. But ultimately, all chemical reactions, there's really 3 reasons why it takes place. You could almost boil down every chemical reaction you see to one of these 3 things occurring. And the 3 sort of reasons a reaction takes place is a solid is formed, which is known as a precipitate, which is sometimes abbreviated as a PPT for precipitate. A formation of water, H2O. And really the third reason why a reaction takes place is a transfer of electrons. And we're going to talk about these different reasons and really the classifications of what's going on in each of these reactions. But as I mentioned a second ago, when you think about reactions, they do really fall into 2 categories. One is what is known as a redox reaction, as we'll talk about. And redox reactions basically account for the transfer of electrons. So that is, again, one of the reasons why a reaction actually takes place is electrons are being transferred, and those type of reactions are referred to as redox reactions. Kind of the other big category of reactions is a double displacement reaction. And a double displacement reaction, as we'll talk about, basically accounts for the other 2 reasons why a reaction takes place. In a double displacement reaction, what essentially happens, as we will see, is you actually start with 2 ionic compounds, and they're ionic because there's like a positive and negative guy together and a positive and negative guy together. And in a double displacement reaction, 100% of the time, the 2 positive guys basically switch partners. So 100% of the time, they just kind of switch partners. And I'm kind of running out of room, so I'll go underneath it with the arrow. And it will make actually 2 new ionic compounds. And when you make these 2 new ionic compounds, one of those other 2 things will happen. One of these guys may be a solid, which is a precipitate. And that is basically, again, one of the reasons why this reaction may take place. You may also do this, reason 1 up there, if you will. You may also do this, and one of these combinations that come together over here will actually make water. And that would be, again, the second reason a reaction takes place. So when we talk about double displacement reactions, they typically account for those two things happening. Typically, either you get a solid that forms or precipitate, or you make water, basically. One you could actually see most of the time. You could actually see a solid form in most cases. It gets cloudy or whatever it may be. Water sometimes is a little bit harder to see because, you know, you made water. It doesn't look too much like different than your solution that's in there, which is water-based. But those are two things. And again, redox reactions basically are for transfer electrons. So like I said, pretty much every reaction will pretty much boil down to one of those three things basically occurring. Any questions on that there? Okay. So let's talk about first redox reactions. Redox reactions are what are referred to as oxidation and reduction reactions. They are, again, the ones, as I just mentioned, responsible for electrons being transferred. And again, this is, you can think of as like a big umbrella to which we can more specifically classify reactions another way or with a different description. But what does redox and all that mean? So there are several definitions of oxidation and reduction, which we will see as we go through this chapter. And we'll actually see it again when we get to organic chemistry. Oxidation and reduction happens a lot. Oxidation essentially means somebody has lost electrons or will lose electrons. There are two other definitions that we will see. It also can mean that it has gained oxygen from reactants to products, or it has lost hydrogen from reactants to products. Now, again, this is probably more where we're going to see it is when we get into organic chemistry, those two definitions. Probably for now, this is going to be really the definition that you'll see the most for oxidation. But again, we'll see the other two definitely when we get into organic reactions, the gaining or losing of oxygen or hydrogen. Reduction basically means the opposite of all those. It will be somebody that gains electrons. It could also mean somebody that has lost oxygen as you go from reactants to products. And it also can mean somebody that has gained hydrogen as you go from reactants to products. Once again, these two are really more of an organic sort of definition that we'll see a little bit later on in the semester. But here again, probably the electron definition is definitely the one that we will see the most. Some people remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Nowadays, people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig and he'll go grr, and you don't have to choose. You can use them all together there and hopefully remember which one those are. Now, when we look at this, the electrons, when somebody loses an electron, do they become more positive or more negative if they lose electrons? They do become more positive, right? Because they gotta have more protons than electrons. And when somebody gains electrons, they become more negative, right? And that's the way you could kind of look at what is happening as you go from like the left-hand side of the arrow to the right-hand side of the arrow. If something, it's really known as the oxidation state or oxidation number, but if you want to think about it as the charge, if you look at the charge or whatever it is on the left-hand side versus the right-hand side, if it kind of gets, again, more positive, it is actually being oxidized. And if somebody gets more negative, it's getting reduced. Easy way to sort of do that is a classic number line situation. Yeah. On a number line, there's positive numbers there to the right of zero, negative numbers to the left of zero. So if somebody gets oxidized, they are becoming more positive. They are moving in this direction on the number line, and that guy would go through oxidation. If somebody's getting more negative, you will actually see him move in this way on the number line, and they would be going through reduction. So for example, if I had calcium over here, and then maybe it makes calcium oxide over here. Do a little that as well, a little balancing action there before I do it. Now, if I look at calcium and oxygen, goes to calcium oxide. By the way, when elements are by themselves, not combined with anybody else, do they have charges? They do not. So this calcium over here has really no oxidation state, really, or a zero charge. The O2 is naturally how it comes, right? That is how you find oxygen, just like how you would find hydrogen, H2, N2, and all those guys. They're diatomic molecules. It also has no charge, basically, and no oxidation state or zero oxidation state. When that calcium and oxygen come together to make that ionic compound on the other side, that is when it gains charges, right? Like we talked about when electrons get transferred here, basically, right? The calcium then will have what type of charge? +2, as it's group number 2 on the periodic table, right? And oxygen, which is group number 6, is -2. So to show you what's happening here and how this sort of number line works, let's just kind of do the number line to figure out what is happening with everybody here. So again, we have our 0, plus, and negative. If we look at the calcium to start with, right, on the left-hand side, the calcium there is a 0, right? And it ends up on the right-hand side at a +2, which means on the number line, it is moving this way. That is moving more negative or more positive, which means oxidation or reduction. It means oxidation, yes? So it's becoming more positive. You're going to lose electrons, which means you have more protons, you become more positive. So the calcium here is going through oxidation, right? If we look at the oxygen, right? So that was calcium. We look at the oxygen, it started at 0. And on the right-hand side, it ended at -2, which means it's moving in that direction, right? It's becoming more negative in this case, right? And that means it should be going through reduction, right? It's gaining more electrons, which is why it's becoming more negative. So this guy is going through reduction. By the way, the good thing about oxidation and reduction is all you have to do is figure out one of them. And by default, the opposite thing is happening to the other guy. They always happen together. So if you could just figure out which one's being reduced or which one's being oxidized, by default, the opposite thing is happening to the other one. So that's kind of a nice thing. You could actually just try to figure out one of them. If you're for sure on that one, then obviously you can figure out the other one by being the opposite. By the way, the thing's being oxidized and reduced in this case on the left-hand side of the arrow. And again, basically what's happening here is those calcium is going to send over some electrons basically to the oxygen here. So again, our calcium is losing electrons, which is why it's being oxidized. And our oxygen is gaining electrons, which is why it's being reduced. By the way, we could actually know this without even figuring much of that out, because between calcium and oxygen, calcium is what type of element? It is a metal, non-metal? Is a metal. And oxygen is a, and when we make an ionic compound, which one always loses electrons? It's always the metal, right? For all those reasons we talked about. So whenever you have an ionic compound, it should always be the metal that loses electrons and being oxidized. It should always be the non-metal that will accept those electrons and being reduced. So with an ionic compound, again, you could always fall back to that metal, non-metal. Metal loses electrons, non-metal gains electrons, and that's pretty much your two definitions of oxidation and reduction. Question on that there. Now, this also works, for example, let's just say in this case, let's say I had, this happening. Maybe there is not a metal and a non-metal you're looking at, but maybe there's just two metals. let's say I had iron with a +3 on the left-hand side, and it ends up with iron with a +2 on the right-hand side. Take a moment and decide, is this going through oxidation or reduction? All right, so let's take a look. So obviously here we have charges we could clearly see. So on the left-hand side, right, the sort of oxidation state or charge of the iron is +3, right? Which is this charge. On the right-hand side, it is +2, which is also its charge in this case. So again, you could go to the number line there and just go, all right, is starting on the left there at +3, which would be maybe about here. And it's ending at +2, which means it does need to go that away, right? And then is that becoming more negative or positive? It's pointing to the negative side. And because it's becoming more negative, oxidation or reduction? It is reduction. This guy is going through reduction, yeah? So again, just simply trying to figure out again, it's really the oxidation state, but we'll call it the charge of those things on each side. And again, whichever way it's going on that number line, if it's becoming more negative, it's going to be reduction. Becoming more positive, going to be oxidation. Question on that there. All right, so this, as we can see here, is again one of the ways that we could overall classify a reaction. We look here at sodium and chlorine coming together to make sodium chloride. We look at the charge of the sodium on the left. That is 0, as it's not combined with anything. This is also 0 because that is naturally the way chlorine comes. Again, not combined with any other element. Now that they do combine on this side to make an ionic compound, that's going to be +1, and this is going to be -1, right? So sodium group number 1, +1. Chlorine group number 7, like we talked about with naming, -1. Once again, if you're not sure, we could put our little number line happening. We'll start with the sodium, which is 0. And the sodium on the right-hand side ends at +1, which means it's going towards the more positive side, oxidation or reduction for sodium. Oxidation, yes. By the way, once I know it's oxidation for sodium, what is chlorine doing? It's reduction. That's all you have to figure out is one of them, basically. This guy is reduction. We could verify that by also going to the number line. The chlorine on the left-hand side is 0. On the right-hand side, the chlorine is -1, right? Pointing to the negative side, becoming more negative, and it is going through reduction. So that's like the simplest way you could kind of figure that out. Just draw an arrow, see which way it's pointing, right? Negative reduction, positive oxidation. You do obviously need to compare the same element on both sides of the arrow. So it's got to be the same element that you're comparing on both sides of the arrow to determine that. So once again, what's happening here is, as we know, the sodium is going to lay up some electrons over to the chlorine and make this ionic compound. And again, on this one, since it's an ionic compound, that's a metal, which we know should lose the electrons, again, be oxidized. That is our non-metal, which should gain the electrons and should be reduced. And ultimately, what is happening here is it is that transfer of electrons that causes this reaction to occur. That need to kind of transfer those electrons is really one of the reasons, and really the reason in this case, that this reaction does take place. This again is a oxidation reduction reaction or a redox reaction. Here we could look at another one that is magnesium, which is 0, and oxygen, which is 0. Again, they are not combined, making that ionic compound. Magnesium is group number 2 on the periodic table, which means it will be +2. Oxygen is group number 6, which means it will be -2. And again, if you're still not sure, we'll do our little number line thing. We'll look at magnesium starting at 0 on the left, ending at +2, which is moving in that direction. Once again, we see that is positive, which means it's becoming more positive, and that again is oxidation that's going to occur here. Also, it's the metal, as we've been talking about, so that is what we expect to happen. Here, the oxygen, once again, starting at 0 and ending at -2, pointing to the negative side, which means it's becoming more negative, which means it had to gain electrons, which is the definition of reduction, and it would be going through reduction. And once again, much like the last one, if you were confident on that, by default, that has to be happening to the other guy. So again, they always occur together. If there's somebody being oxidized, there's somebody being reduced, and vice versa. So they are always work sort of together. Once again, this is our electron transfer happening from our magnesium over to our oxygen. And again, the reason why this reaction is taking place. Any questions on that there? Now, again, we will see these sort of definitions a little bit later on when we get into organic. And really in organic chemistry, there's not a lot of metals involved, which is why we look at hydrogen and oxygen sort of definition of oxidation and reduction rather than sort of charges on the left and right and electrons. So in this chapter, probably not too much of hydrogen and oxygen, but definitely we will see it later on in organic chemistry. But here, as I mentioned, if somebody gains oxygen as it goes from left to right, it's being oxidized, hence the name oxidation. It gains oxygen basically. And if it is being reduced, it will lose oxygen. So if we look at the sulfur here, it is going from 2 oxygens, and the sulfur over here ends up with 3. So it has gained electrons there. Not electrons, it has gained oxygen as it goes from left to right. So this is going through oxidation as it has gained those oxygens. And obviously by default, this would be going through reduction in this case, as obviously the oxygen sort of disappears. So it definitely lost oxygen, is no longer there on the other side. Over here, we look at the copper, 1 oxygen, copper over here, no oxygen. So it has lost oxygen as it goes from left to right, which means that it is going through reduction in this case. The hydrogen, no oxygen here, but gains oxygen here. So that is going through oxidation. So you can look at oxygen and hydrogen as examples. But in this particular example, there is actually a metal, which means we could actually still do the metal look at it. That copper on the left-hand side is copper what? Roman numeral 2? Seems good. I got those fingers up. Sounds right. So that's Roman numeral 2 there because the oxygen is -2 there, right? And that would be +2. Copper over here by itself is 0. Again, any element by itself, not combined with anybody else, 0. So if we just did our number line for the copper started at +2 over here and ended at 0, which is going towards the negative side, which means it is being reduced. Yeah, so in this case, because there was still a metal, you could kind of still do the charge on both sides. And by the way, if I did that and I was able to do the charge and figure out this is reduction, by default, that would mean this guy has to be oxidation, right? So again, they always occur together. You just need to accurately figure out one of them, and you'll know what's happening with the other thing. Any questions on that there? And hydrogen as well. Losing hydrogen is going from reactants to products is oxidation, and gaining hydrogen is reduction. So if we look at our carbon here, I can say copper again, but carbon, it has hydrogen in it. Over here, not so much hydrogen, right? So it has lost hydrogen, which means it is oxidized, right? And by default, that would mean this guy is reduced in this case. By the way, I could also use the oxygen definition here, right? The carbon went with no oxygen to oxygen, which means it also gained oxygen, which is another definition of oxidation. So, sometimes you can look at more than one sort of definition, but they all should tell you the same thing, which one's being oxidized and which one's being reduced. So once again, probably in this chapter, more the charge is what we'll see. But again, when we pick up organic chemistry, it's all about hydrogen and oxygens gaining and losing in terms of reduction. So we definitely will see it a little bit later on when we get into those chapters. Any questions on that there? Okay. And by the way, even though we sort of look at hydrogen and oxygen in those cases, what's ultimately still happening is still a transfer of electrons, even though we're kind of looking at oxygen and hydrogen for those purposes. As we talked about, those are the 3 driving forces. Again, why a reaction occurs, solid being formed, water being formed, are again the transfer of electrons, which is really our redox sort of definition. So let's talk about some more specific ways we could classify redox reactions. So under the big umbrella of redox reactions, a more specific way you could classify a reaction is either a synthesis or combination reaction. And in a synthesis or combination reaction, it is basically two things make one thing. It's basically what you're looking at. So two things will make one thing. So here we have two things makes one thing. So synthesis, combination. Two things make one thing, synthesis or combination. That is a more specific classification of a redox reaction that's still occurring. If you look at the water formation, hydrogen by itself is 0. Oxygen by itself is 0. When hydrogen and oxygen get together to make water, oxygen is -2. Hydrogen is +1 in this case. And if you go to our number line here, we could see for our hydrogen, it is starting at 0 and ending at +1, which means our hydrogen is actually becoming more positive. And that would mean the hydrogen is going through oxidation or reduction. It becomes more positive. Oxidation. Yeah. By default, that would mean the oxygen is going through reduction, right? The opposite. And we can see that with the oxygen is starting at 0 and ending at -2, becoming more negative, the oxygen. And that again is your definition of reduction. So a more specific classification, two things make one thing, is a synthesis or combination reaction. It falls under the bigger classification of reactions, which is it's a redox reaction. I would say 9 times out of 10, people would probably call it a synthesis or combination reaction, but ultimately it is under that sort of redox umbrella. Any questions on that there? The next type of reaction is pretty much the opposite reaction. It is a decomposition reaction, and that is when you start with one thing and make multiple things. So if you start with one thing and make multiple things, that is the way you can recognize it as a decomposition reaction. If you run an electrical current across water, you will break it apart into hydrogen gas and oxygen gas. That again is one thing makes two things in this case. You take a little mercury 2 oxide and heat it, get some mercury and oxygen occurring. Two things make one thing. Again, classic decomposition. So synthesis or combination, you put it together, and decomposition, you break it apart, basically. Still a redox reaction happening here. It is still under the big umbrella of redox. If we look at our water going in this direction, that is +1 for the hydrogen, -2, 0, and 0 in this case. In this case, when we break apart the water, the hydrogen is starting at +1, which is over here, and ending at 0. In this case, going backwards, the hydrogen is actually becoming more negative, and it's the hydrogen here that is getting reduced, and the oxygen is getting oxidized in this case, because it's the opposite of what you did, right? So if you kind of flip the reaction around, everybody switches basically places there. Oxygen starting in this case at -2 over here, ending at 0 as you go this way, becoming more positive when you go backwards here. Same thing with the mercury over here. That is mercury 2. That is mercury with no oxidation state. So if we look at the mercury, mercury is starting in this case at +2 and ending at 0. Mercury is being reduced in this case. The oxygen is being oxidized. So again, the big classification of this type of reaction is still a redox reaction. Ultimately, what is happening here is still transfer of electrons, which is why this reaction takes place. But in this case, we're actually breaking it apart, right? So one thing makes multiple things. Any question on those two types of reactions? They're basically opposites of each other. The next type of reaction, which also falls under a redox reaction, is a single replacement reaction. And in a single replacement reaction, you have basically one thing, and that could be a metal, for example, plus an ionic compound, which is a positive and negative guy. And in this case, the metal actually has no charge to start with because it's all by itself. Like you had a piece of zinc metal just by itself. And although the metal is not starting with a charge, we do know that when a metal makes a charge, is that going to be a positive charge or a negative charge when it makes a charge? Positive. So what happens in this reaction is the metal will actually go in and kick out the positive guy. And when it kicks out the positive guy, that is when that metal will then gain a positive charge and actually hook up with the negative guy there. And the guy that gets kicked out will come out by himself with no charge. So what's really happening is the A is sending some electrons over to the B in this case, and that is what's going to cause it to go away. You could also do this reaction with a nonmetal plus an ionic compound. And a nonmetal here, again, by itself will have no charge. But when a nonmetal makes a charge, it will become positive or negative. Nonmetals become negative, right? Upper right of the periodic table. They're the ones that will gain those electrons. So when it comes in, it will actually kick out the negative guy in this case. And when it kicks out the negative guy, it will then get a charge of negative charge. And that guy that gets kicked out will come out by itself with no charge in this case. Now, in order for this reaction to actually take place, whatever is coming in to kick somebody out needs to be more reactive than when it's replacing. So whatever is coming in, like this guy or this guy, needs to be more reactive than what it is replacing. So for example, if you did this guy here, which is zinc coming in and kicking out hydrogen, it will make hydrogen gas. You'll see bubbles occur in your test tube. That's the hydrogen gas being made. And that means that zinc in this case is actually more reactive than hydrogen. If you did this exact same reaction with copper, you will get no reaction because when copper comes in, it's actually less reactive. So this reaction will not take place. For example, if you had an old penny, which is made of pure copper, and you file the hole in it and you put in hydrochloric acid, it's going to still be there when you come back. Take a new penny, you file a hole in it. Inside a new penny is zinc. And if you put that into your hydrochloric acid, you come back, you're going to have a hollow penny because it's going to eat everything on the inside away. And the outside will be still okay because the outside is still copper-ish in most cases. And again, for whatever's coming in needs to basically be replaced. By the way, when hydrogen comes out, it comes out as hydrogen gas, which is how naturally hydrogen comes out as, and that's why you see those bubbles. This is a single replacement reaction. It is still a redox reaction. If you want to look at just the zinc, for example, the zinc is 0 over here. The zinc on the right-hand side is the zinc with the charge because it's hooked up with the chloride. That means in this case, the zinc started at 0 and ended at +2, which means it is pointing in the positive direction. The zinc here is being oxidized. Yeah. What is being reduced in this case? Is it the hydrogen or the chlorine, or both? Let us see. How about the hydrogen on the left? It is actually +1 in this situation, and hydrogen by itself is 0, which means when we look at the hydrogen in this case, it is starting at +1, which is here, and ending at 0, becoming more negative. And it is the hydrogen here that is actually getting reduced in this case. What's happening with the chlorine? Chlorine on the left-hand side has what type of charge? minus 1. It is group number 7 on the periodic table, right? On the right-hand side, the chlorine has what type of charge? Minus 1, because it's still group 7, right? Did anything change with the chlorine? Nothing. It's what we call a spectator ion. It's just hanging out, having a good swim, but not doing anything, right? So it's just kind of there to balance out the charge. So it's really the zinc and the hydrogen changing in this reaction. The chlorine is not doing anything. It's just kind of hanging out. Any questions on that? So again, falls under the big category of redox reactions. A more specific classification for this reaction is a single replacement. Some people call it a single displacement. It don't really matter, but single replacement reaction in this case. Any questions on that there? Yeah. It has a few reasons why, but yeah, some of those periodic trends that we talked about. There's actually what is referred to, and it's not so important for us, but there is what's referred to as an activity series, and just in case it pops up somewhere, but I don't think it will. But an activity series really is just a list of a bunch of elements, and usually you have hydrogen like in the middle or something, and then you got a bunch of elements above it, you got a bunch of elements kind of below it. And when you look at this activity series, anything that's higher on the list will replace anybody that's lower on the list. So if you were looking on that list, you would see zinc is higher than hydrogen, and it would replace it because it's higher on the list than hydrogen. If you look on this list, you would see copper is actually below hydrogen, and it being is less reactive. So this is what's known as an activity series, and usually a basic one is just like that. It's just a list of elements, and usually hydrogen is in the middle. And again, anybody higher on the list is lower. For like nonmetals, for example, Group 7 is actually the activity series for group 7 on the periodic table. As you go up, based on those periodic trends, becomes more reactive. So fluorine would replace chlorine. Chlorine would not replace fluorine because it's lower on the list. Bromine would replace iodine. Iodine would not replace anybody else above it and stuff like that. So for like the nonmetals, it's usually the halogens you look at, and you can actually use the periodic table on group 7 as like an activity series. And again, it increases as you go up. And it's really based on those periodic trends we talked about in that chapter, because right, everything as you go up and to the right wants to give away, hold on to their electrons and grab electrons, makes them super reactive. And to answer your other question, as you go down to the left, we got everybody that wants to give away their electrons, right? So it makes it kind of more reactive. Yeah. Other questions? All right, so what we're going to talk about next, though, is a blank screen. No, let's get rid of that there. We're going to talk about the other big classification of reactions. So redox is basically your synthesis, your single replacement, and your decomposition. A precipitation reaction falls under double displacement reactions. And always when you have a double displacement reaction, and how you can recognize it as being different than a single replacement reaction is you have two ionic compounds. So in a single replacement reaction, you got just one. In a double displacement, like the name implies, double means two. You got two basically ionic compounds here. And always when you have two ionic compounds, 100% of the time, they're just going to switch partners, basically. So they're always just going to switch partners and make new ionic compounds on the other side. And again, as I said earlier, we'll have our A and our D, for example, and our C and our B in this case. And again, if one of these guys makes a solid, which is known as a precipitate, then you get a more specific classification of this type of reaction, which is known as a precipitation reaction. So a precipitation reaction is a double displacement reaction that results in a solid being formed. As a result here, if you take some potassium chromate and you mix it with some barium nitrate, you will form some barium chromate, which is a solid. And that presence of a solid, which is known as a precipitate, makes this a precipitation reaction. It is still a double displacement reaction. That's a positive guy, negative, positive, negative. If you were to look at the ions here, that is basically K plus and CO4 2 minus. The basic ions of this guy is Ba2 plus and NO3 minus. These two guys switch partners, and these two guys come together as they switch partners on the other side of the arrow. Super important, if you're asked to write what's on the other side of the arrow, you actually start with the right formula. So when I take K plus and NO3 minus, I just need one of each, which is why I get that KNO3 formula here. When I take the barium, which is +2, and put it together with the chromate, which is -2, that is why I get one of each of them when I put them together. Do I care all that much about the extra 2's on the left-hand side? Not until I put it together correctly. Then I care about the missing 2's, and I need to balance it. So I think I talked about this when we were talking about balancing equations. This is a very common error that people make. If they had something like this, they would look at it and go, perhaps, I don't know, like K2NO3 2 and like maybe BaCrO4, and they'll try to balance and write the formulas at the same time, and you'll get the wrong formulas and it will not be properly balanced. So if you have to predict what's on the other side of the arrow, and I don't know how much I would ask you to do that here, but if you did, you need to make sure you always start with the formulas first, just like you were doing nomenclature, get everything settled, and then you should go back and change the coefficients and balance the equation. And you also should look at it like this. Even though there's 2 potassiums in that first guy, the basic ion of potassium is K+. That's what you start with, just the basic ions that make up those things, and then put them together correctly, and then balance them. Any questions on that there? All right, so precipitation reaction forms a solid, which is, again, one of the 3 reasons why a reaction takes place. It is specifically called a precipitation reaction because it makes a solid. It falls under the big umbrella on a rainy day of double displacement reactions, and it is ultimately a double displacement reaction that's taking place here. And again, it is always recognized by having those 2 ionic compounds. And as soon as you see 2 ionic compounds, you should always just think about switching partners, basically. And that's always what it's going to be on the other side. Again, in a single replacement, like we just talked about, you have just an element by itself, no partner, and an ionic compound. So just 1 ionic compound. And again, the names help you remember that. Perhaps single, just 1 ionic compound, double 2. Yeah, 2 ionic compounds for you to do that. Any questions on that there? Here is an example of a strong acid and strong base coming together. This is hydrochloric acid, which is an acid and a base. And typically when you take an acid and base, especially a strong acid and a strong base, which is what this is, you basically make 2 things. You make water and what is referred to as a salt. And a salt is a fancy word. I don't know how fancy it is, but it's a fancy word for an ionic compound. It's basically a metal and a non-metal together is basically what a salt is. This type of reaction is called an acid-base reaction. It's also called an acid-base neutralization reaction. Acid-base neutralization reaction, because you basically make water. Where does the water come from always in this situation? The water always comes from the hydrogen from the acid, because that's the definition of an acid, H plus basically. And the OH minus from the base, which is the definition of a base, something that makes OH minus. So that gives me 2 hydrogens and an oxygen. That makes my water. And what does the other part of it come from? It's basically what's left over after you do that. It is this guy, which is K plus, and this guy, which is Cl minus, making KCl in this case. So 100% time you got strong acid, strong base, H plus from the acid, OH minus from the base, makes your water. Whatever's left over you put together, and that's what makes your salt. A salt really in this case is also a spectator ion. It's just hanging out, having a good swim. It's really not doing much in this case. But a couple of things are happening here. This is still a double displacement reaction. And it is because, as you can see, hopefully, that's a positive, negative, and basically we switch partners here, right? And that is your ultimate double displacement reaction that occurs. It is also the third reason why a reaction takes place, because what did I make on the right-hand side? I made water, yeah. So again, that's one of the three reasons why a reaction takes place. You basically made water. If you were looking at this, you probably wouldn't see it because water doesn't look all that much. It looks like everything else, unless you maybe put an indicator or something in there. You may help you understand it's an acid-base one. Any questions on that? So under the double displacement sort of umbrella, we have precipitation reactions, which make a solid. We also have acid-base neutralization reactions, and that is making water. And under our redox, we have our electrons being transferred, which is our synthesis, our decomposition, and our single replacement. There is one more reaction that actually does fall under redox reactions. And this guy, which is a combustion reaction, falls under the redox umbrella. And I would say, to be truthfully honest with you, probably 9 times out of 10, maybe even more, if somebody's talking to you in your everyday conversation about a combustion reaction, I don't know what kind of conversations you have, but maybe you're having that conversation. They are most likely talking to you about the organic combustion reaction, which is you take an organic guy, and usually an organic guy contains carbon, hydrogen, and oxygen, like that, methane, like some propane happening there, right? Methane, propane, when you put a spark with those, you get fire, yeah? Like when you light a Bunsen burner, you turn your barbecue on, whatever it may be, right? All those kind of things. And if you take that organic compound and you add oxygen to it, usually a spark along with it will give you some fire and heat. You will always make these things. You will always make CO2 and water. So if you see CO2 and water on the product side and you see O2 on the reactant side, it is probably an organic combustion, especially if you got some type of carbon, hydrogen, oxygen thing that you are starting with. That is probably, like I would say, most of the time what people are talking about with a combustion reaction. There is an incomplete combustion that can form carbon monoxide instead of CO2 and water. But I say most of the time, if they don't say it's an incomplete combustion, then CO2 and water is basically what you're going to do. Now, to be truthfully honest with you, just in general, if you're rolling with combustion, the basic only thing that you technically need is O2 there. That technically is all you need for it to be considered a combustion reaction, even though most people will be talking about these type of combustion reactions. But technically speaking, if you had O2 on the reactant side, it can be classified as a combustion reaction. So what that means, for example, is if you looked at this one that we saw maybe a little bit earlier, magnesium plus some oxygen makes a little magnesium oxide. This is two things that make one thing, which means it can be classified as a synthesis reaction, right? Or a combination. It is also a redox reaction, as we saw earlier, right? 0, 0, plus 2, minus 2. Could also be classified as a redox reaction because definitely there's electrons being transferred from the magnesium to the oxygen. And what else is there? There's an O2, so why not go for the trifecta here and go for a combustion reaction as well? So as I was saying earlier, you could actually, for reactions, classify them in multiple ways. The best piece of advice is to choose the best classification for whatever situation you're looking at. I would say most people, when they're classifying reactions, will classify them as either a synthesis, a decomposition, a single replacement, a double displacement, or a combustion reaction. I think I got them all. And that's probably most of the time the classifications you'd use. But again, you can classify the same reaction multiple ways, depending on maybe what you're looking at. Any questions on that there? Now, just to summarize what we talked about, we have these big classifications, which is redox, which is the transfer of electrons. More specific classifications underneath this guy, again, is your synthesis reaction. Again, two things make one. Your decomposition. One thing breaks apart into many. Your single replacement reaction. Something by itself plus one ionic compound comes in and kicks out, maybe if that's a metal, making your AC and your B. And your combustion reaction, which again, most people, organic plus some oxygen, CO2 plus water, are just basically O2. And again, all those guys under the redox category are more specific ways that you could classify a redox reaction happening. On the double displacement side, it will take care of the other two reasons: the formation of a precipitate or a solid, and the formation of water, are again the two things that you get out of that guy. And this is always the same type of reaction. Double means two, so two ionic compounds switching partners as they go across. And again, if one of those guys forms a solid on the product side, it can more specifically be called a precipitation reaction. And if one of those guys forms water on the product side, it most likely will be more specifically a acid-base reaction. So again, kind of our two big umbrellas covers all three reasons really why a reaction takes place. And under those big umbrellas, we could have more specific classifications of these type of reactions. Any questions on any of that there? Okay, we're going to continue on here, and we're going to talk about some calculations that are important, and then we're kind of put everything together and talk about calculations you could do with reactions. So the next thing we're going to talk about is molar mass and our friend Avogadro and his number. And one of the first things we're going to talk about is actually the mole. And the mole is a sort of name in chemistry that does represent something. So much like in life, we have words that represent a certain amount of something. So if you say you got a pair of shoes, that usually means you got two shoes, I hope. If you got a dozen roses, you got 12 of them. If you got a gross of pencils, a 144. Not sure they give out pencils anymore. But the mole is actually abbreviated, by the way, MOL. And the mole needed some type of abbreviation, so they dropped the E. Now, it's really important when you do see MOL that you realize that it is the mole and it is not molecule. And that, again, is a super common error that people make. They just see the MOL and think, oh, it must just be like an abbreviation or something for molecule, and it is not. So in chemistry, if they want molecules, they will write molecules, yeah? So they'll write the word molecules. So if you see MOL, it is moles and not molecules. So in chemistry, we have a word for that representation, and 1 mole of anything will actually equal 6.022 times 10 to the 23. And the units associated with this number does change. It can be particles. It can be atoms. It could be molecules. It could be pizzas, in case you're hungry. Maybe your shoes, so you could go walk to get your pizza, whatever it may be. Although the occasional pizza question may come around, but probably in chemistry, these are going to be the 2 units that you're going to see the most, which are atoms and molecules. So again, just like we say a pair of something means 2, if somebody says I have a mole of something, it means you have 6.022 times 10 to the 23 atoms. Or if you have a mole of a molecule, you have 6.022 times 10 to the 23 molecules of whatever it may be. That is what is known as Avogadro's number. And Avogadro's number is 6.022 times 10 to the 23, named after a guy named Avogadro. You could do it for anybody on the periodic table you like. 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. 1 mole of carbon would be 6.022 times 10 to the 23 atoms of carbon. You could also do this for molecules. If you had 1 mole of water, it would equal 6.022 times 10 to the 23 molecules of water. If you had 1 mole of methane, you would have 6.022 times 10 to the 23 molecules of methane. Here for methane and water, because they are molecules, we use the units of molecules for Avogadro's number. For hydrogen and carbon or anybody else on the periodic table, if it's just the element by itself, we use atoms for it. So the units of that number can definitely change, but those again are probably the 2 most common ones that you'll come across in chemistry. What do we use Avogadro's number for? Frankly, it's just a conversion factor. So it is a conversion factor that lets you convert from moles to either atoms or molecules, or backwards. If you're starting with atoms or molecules, you could convert into moles. How do you do that? Dimensional analysis like we did originally, right? So if you have moles, you would want to use Avogadro's number as a conversion factor, and opposites cancel, which means a mole on the bottom gives you Avogadro's number up on top. And again, these could be atoms or molecules. The moles will cancel. You'll get to atoms. And again, you could also do this with molecules as well, depending on the units that you need. And if you're starting with atoms or molecules, you would put Avogadro's number in the opposite location, which means it would go on the bottom. And you would go 6.022 times 10 to the 23 atoms is a mole. The atoms or molecules will cancel, and you will be left with a mole. So really, Avogadro's number is a conversion factor that really allows you to go between those units. And again, you want to use it as a conversion factor, and that pretty much means you could always do it like we did with conversion factors, put the moles on top, the atoms or molecules on the bottom, or flip it around and go Avogadro's number up on top with atoms or molecules and a mole on the bottom. So again, you can use it just like any conversion factor we use when we're talking about conversion factors and dimensional analysis. Question on that there. Should you use Avogadro's number in every calculation? The answer is definitely not. And what happens is a lot of people go, I learned this number, I probably should use it somewhere. And they end up using it wrongly, but hopefully wrongly correctly in a sense. They will oftentimes divide by Avogadro's number at the beginning and then multiply by Avogadro's number at the end, which cancels each other out. You actually get okay sometimes in that situation. But you should never use Avogadro's number unless it's necessary. How do you know if it's necessary? You want to look for keywords, like either you're given a number that says atoms or molecules. That should be your key of, I should use Avogadro's number somewhere. Or you're asked to solve for something that's in atoms or molecules. That should be your key. Avogadro's number needs to come into play somewhere. Doesn't mention any of that. Just leave Avogadro's number on the side. Don't use it. So those are the kind of the keywords that you want to think about. Did they give me atoms or molecules, or did they want me to solve for atoms and molecules? I should use Avogadro's number. If they don't mention any of those things, then again, don't use Avogadro's number. So again, that's sometimes a pitfall a lot of people fall into, is they want to try to incorporate it into like every calculation. And there is, again, a certain place where you should do that. Now, as I mentioned, Avogadro's number represents that 6.022 times 10 to the 23. And you could do it for anybody, again, that is from the periodic table. You could do it for any type of molecule or compound. You could use Avogadro's number. The conversion factor that we use probably the most, to be truthfully honest with you, is molar mass. And you probably will use molar mass more than you would use Avogadro's number in most cases. And molar mass has the units of grams per mole. The number always stays with the grams part, and the mole is always 1. So use how many grams there are in a mole. The molar mass can be found on the periodic table. It is the number that's on the bottom. And earlier we talked about that number being the atomic mass in AMU. And it is technically the atomic mass in AMU per atom. But nobody goes to a scale or a balance and see AMU listed, right? You see grams usually listed. So we actually use it in a more convenient unit for us, which is as the molar mass in units of grams per mole. The good thing is, numerically speaking, value-wise, the number you see on the bottom in AMU per atom and the molar mass in grams per mole, same number. Yeah, so it is the same number. And I would say 99 times out of 100, molar mass is what you're going to be using in a calculation, maybe even more than that. But that's definitely what you're going to use. When you do go to the periodic table to pull these numbers off, typically speaking, it is 4 significant figures is what you want to use. So depending on your periodic table, this one is rounded to 4, which is typically what you use. But some periodic tables will have a lot more numbers down here, or maybe some less. But typically speaking, you want to round the numbers that you pull off the periodic table to about 4 significant figures is typically common practice to use. Now, as I mentioned before, molar mass and atomic mass are numerically the same value. And it is also a conversion factor, essentially. So you could take anybody from the periodic table and look underneath them, like we see here with carbon. And that would mean that there are 12.01 grams of carbon and 1 mole of carbon. The number off the periodic table is always the grams. It's always 1 mole. And that would mean the molar mass of carbon is 12.01 grams per mole is the molar mass of carbon. And again, number with the grams, mole is 1. It is a conversion factor. So you could write, for example, for carbon, 12.01 grams over a mole. And you could use it with the mole on top, 12.01 grams. So you could use it as a conversion factor. And it is the conversion factor that we use to go from grams to moles and moles back to grams. So if you have any type of conversion where you need grams and you have moles, molar mass is the conversion factor you want to use from the periodic table. If you have grams and you want moles, or moles you want grams, again, periodic table is where you're going to get that. You can, just like Avogadro's number, apply molar mass to an element by itself. You could also apply it to a molecule or a compound. So if I had something like water, I would go to the periodic table, find hydrogen, 1.008. I know your book probably goes 1.01. I don't like it. 1.008. Oxygen there, maybe 16. And what we would do to get the molar mass of water is, frankly, just add up all the parts from the periodic table. So there are 2 hydrogens. We would take 2 times the molar mass of hydrogen. So that's hydrogen, basically. We would add it to the molar mass of oxygen, which there's just 1 of, and that would be 16 grams per mole. And that would give us 18.02 grams per mole as the molar mass for water in this case. And again, that really is 2 conversion factors you could use for water. That is 18.02 grams over a mole or a mole is 18.02 grams. You will not use both conversions like a normal dimensional analysis problem. You will pick whichever one you need. And remember, opposites cancel, right? So units in opposite locations will cancel just like we did before. If you did something like methane, CH4, there is one carbon, which is 12.01 from the periodic table, which is right here. And that is our carbon. We would add it to 4 times hydrogen's molar mass from the periodic table, which is 1.008 grams per mole. Grab my calculator, it's late, but it's 17 and some change, I think, but I'll go for it. Ah, 16, that'll work. So we got 16.04 grams per mole. That would be our molar mass of CH4. And again, you could use that as 2 conversion factors, 16.04 grams per mole, or a mole is 16.04 grams. So again, you would not necessarily have to use them both, and you probably shouldn't. So for example, let's just say that I had 52.5 grams of CH4, and I want to know how many moles of CH4 that would be. And again, I see MOL, which is moles, not molecules, right? So that is moles. And we would do it just like a dimensional analysis problem, 52.5 grams of CH4. And once again, it's not written as a fraction, but I can now see grams are up on top, which means between my 2 conversion factors here, the one on the left, the one on the right, which one would be appropriate to use in this case? The one on the right, it has the grams in the opposite location, right? Dimensional analysis, opposites cancel. So we would use that just like a regular conversion problem. The grams will cancel. Once again, a reminder, we're multiplying what's on top, right? And we're dividing what's on the bottom, just like we did in chapter 2. And in this case, 52.5 divided by 16.04 would give me 3.273067. A lot of numbers. By the way, significant figure-wise, where should I end up? That is how many? 3. And that is this one we really should look at. So I really should end up with 3.27 moles, just like we did with dimensional analysis, right? So molar mass can be found from the periodic table. That is basically where you get this conversion factor from, right? So instead of finding it in like a book table, you find it on the periodic table. You could do it from any element that is by itself. You do it for any type of compound. You just add up all the parts, and that gives you how many grams there are per mole. And you just want to use it as a conversion factor. Any questions on that there? How does Avogadro's number and molar mass relate to each other? Well, they relate to each other like this. If I have, for example, here hydrogen, which is 1.008, and I have 1 mole of hydrogen, right? That means that there are 1.008 grams of hydrogen and 1 mole of hydrogen, right? That is the molar mass basically from the periodic table. And if I have 1 mole of hydrogen, how many hydrogen atoms would I have? 6.022 times 10 to the 23 atoms of hydrogen, right? If I have water, we just did 18.02 grams of water equals 1 mole of water. How many molecules of water would I have? 6.022 times 10 to the 23 molecules of water. What is the thing that ties together grams and atoms or grams and molecules? The thing that ties them together is moles, yeah? Moles is the middle step to get you from one end to the other. So If you have grams and you eventually want to get yourself to atoms, you need to go molar mass from the periodic table to get to moles. Then you need to go Avogadro's number, right? To get yourself from moles to atoms. Same thing here. If you started with grams and want moles of water or a molecule, you need to go molar mass to get yourself to moles and Avogadro's number to get yourself to molecules. Also, by the way, if you started out on the right-hand side there, you need to go from atoms to moles. That's Avogadro's number. Moles to grams, molar mass. So it works the same going backwards as well. Same thing here. Molecules to moles, Avogadro's number, moles to grams, molar mass. So once again, molar mass from the periodic table, bottom number, how many grams there are per mole. If you have something that is a compound, you just need to add up all the parts. Avogadro's number, a fixed number of 6.022 times 10 to the 23 used with molecules or atoms. Any questions on any of that there? And once again, if there is no mention of atoms or molecules, don't do the Avogadro's number part. Yeah. So as we talked about, these are really just conversion factors, and molar mass, extremely important in chemistry, used more than probably any of them, is using that molar mass from the periodic table. Grams to moles, moles to grams. Those are two conversions that are the start of a lot of calculations, taking grams to moles, and they're also a lot of times the ending part of a calculation, like moles to grams. So they're used a lot in chemistry, that molar mass part of it. All right, well, let's try some, shall we? So why don't you give it a go here? We want to know in the first one, how many moles of helium are in 5.46 grams of helium? In case you can't see the periodic table, let me give you what we got going on here for helium, 4.003, and for zinc, 6538. We'll use the new number, why not? One of the few numbers have changed over the years, 6538. Used to be 39. All right, just take a few moments there, grab your calculator. It's been a while. Say hello to it and see if it works good, hopefully. Okay, let's take a look and see how you're doing. Let's start with the first one. In this case, we're looking for how many moles of helium are there in 5.46 grams of helium. First question is, do I need Avogadro's number here? The answer is no. There's no mention again of atoms. There's no mention of molecules. You do not need Avogadro's number. A reminder, moles and molecules are different things. This is your basic conversion here of grams to moles. And as we talked about, that is your molar mass from the periodic table that allows you to do that. You would go to the periodic table, you would find helium, you would see that number there. And again, that means that you have 4.003 grams of helium in a mole of helium. Our helium's molar mass is 4.003 grams per mole is typically the way it's written. Again, really, that is a conversion factor that we could use 4.003 grams over a mole, or we could put the mole up on top and 4.003 grams. We're just going to take a dimensional analysis approach because remember, it will kind of work itself out for you if you do that. Again, here, basically grams are up on top. So opposites to cancel, which means right-hand side is what we want to use here. We're essentially dividing here by the 4.003 grams per mole of helium. Grams will cancel. And again, we're going to divide what's on the bottom and multiply what's on top, just like we did previously. And in this case, looking at this guy, 1.36 moles of helium in this case. Yeah. Any questions on that one there? Okay, looking at the second one here, we want how many grams of zinc are there in 0.256 moles of zinc? Do we need Avogadro's number on this one? We do not, and once again, that is not molecules, that is moles. So again, that's really important to remember. So this is actually a mole to gram conversion, also molar mass, basically from the periodic table. We're going to grab the molar mass right there. And again, that would tell us basically the molar mass is 6538 grams per mole is the molar mass of zinc. We could also flip this guy around and again use it as a conversion factor in the other sort of degree there. We'll do our dimensional analysis here. We got 0.256 moles of zinc. Once again, if it helps you, put it over 1 so you can see that the moles are up on top. In this case, left conversion or right conversion I need to use here? Which one? I need to use the one on the left, opposite, right? Puts moles on the bottom. And grams go up on top. Once again here, the moles will cancel, going to multiply and divide. In this case, really just multiply in this particular case. And that would get you 16.7 grams of zinc in this case. Both times significant figures based off of really the original number there, which has 3. You could kind of think of molar mass as an exact number, even though maybe it's not particular, but you'd probably want to look more at the original number in this conversion. Question on any of those conversions there. So again, molar mass periodic table, that is definitely where you want to get it from. All right, let's take a look at another one here. What is the mass in grams of one gold atom, AU? And from the periodic table, AU is 197. All right, so take a few moments there. We're looking for what is the gram of one single gold. Okay, so let's take a look at this one. What is the mass in grams of one single gold atom? First question is Avogadro's playing a part in this calculation? It is, because the key word here is atom, right? So we're given atom. That should tell you you need to use Avogadro's number somewhere along the way. In this particular case, we have atoms. We eventually want to get to grams. What is the unit that ties both of those together? It is the moles, right? So now we can think about how we could get there. I know atoms to moles, that's our friend Avogadro, right? And moles to grams is from the periodic table and the molar mass, right? So that is like the pathway we want to go to sort of get us there. So we need a couple of really conversion factors to allow us to do that. Obviously, we need Avogadro's number, which would mean in this case, 1 mole of gold would contain Avogadro's numbers worth of atoms, pretty much in this case, right? And again, that's going to give us our 2 conversion factors that we could use. 1 mole of gold over 6.022 times 10 to the 23 atoms. Or we could use Avogadro's number up on top as well, over 1 mole. Right. So that is where we're going to kind of try to use to go that pathway. Molar mass, once again, always going to come from the periodic table, right? And it's that number on the bottom. And that number for gold means that we have in 1 mole of gold, we got about 197 grams. And that would give us our molar mass of gold of 197 grams per mole for gold. We also could flip that around and use it as a conversion factor the other way if necessary. We could flip it around and go a mole is 197 grams, right? Now, again, we're going to start, and remember that if you set it up dimensional analysis like we were talking about and have done previously, it does help you with should I multiply or divide if you're not sure, right? So again, we just want to put things in opposite locations. So we'll start with what they gave us, which was 1 gold atom. And once again, if it helps you, put it over 1. And now you should hopefully see that atoms are on top, which means should I use the conversion factors up here on the left or the one on the right? Which one should I use? Which one will put atoms in the opposite location? It is the one on the left, right? That has atoms in the opposite location. That's going to put my Avogadro's number right about here. And my 1 mole of gold up on top. The atoms will cancel at this point. If I stop the calculation right at this point, the units I'm in are what? Moles. I basically have now gone halfway across, right? So I'm stopped right there. I now need to go the rest of the way, and that's going to be our molar mass conversion to help us do that. You can do one of two things at this point. You could get an answer if you want. And if you do get an answer at this point, I wouldn't round too much, but if you want to, or you could just continue on with the calculation and still do the opposites cancel, right? So I'm going to continue on with the calculation. And again, in this case, by doing it this way, I could clearly see the moles are on top or bottom in this case. The moles are on the top, which means to get rid of moles, I need to put them on the opposite location, which would be the bottom. So now when I look at my 2 options here for conversion factors from the periodic table, only one of them should work correctly, which is, in this case, the one on the left, which has the moles on the bottom. We will do that. 197 grams up on top, moles on the bottom. The moles will cancel. The only unit left standing at this point are grams, which is good because that's what we're looking for. And because we set it up this way in dimensional analysis, the only thing we have to remember, like we talked about previously, up on top we multiply, on the bottom we divide, right? By the way, when you put Avogadro's number into your calculator, you also want to make sure you use your exponent button, right? So just like we talked about with scientific notation, you definitely want to make sure you're using your exponent button when you punch it in. So that means essentially we have 1 times 1 times 197. You could hit equals. You're going to divide it by what's on the bottom, which is basically Avogadro's number, 6.022 exponent button, 23. Going to give you 3.271 times 10 to the minus 22 grams of gold. Once again, a reminder, basically to punch this in, 197 divide 6.022 exponent button. It is a positive exponent, so no negative button, and equals. Yes, so again, that way. Really, because everything else on top is 1 and everything else on the bottom is 1, so you don't really have to punch those into your calculator at that point. First off, any questions on the calculation? And like I said, you absolutely could have done the first part of the calculation, got an answer, and just kind of set it up again for the second part and get an answer is perfectly fine in this case. In terms of significant figures, I went with 4 based on the molar mass in this case. And that's because 1 gold atom technically would be like something you would count, even though you really can't by your naked eye there. But it would be kind of more of an exact number. So you really could have laid up as many significant figures as you wanted really on this particular case. Question on that calculation. All right, let's try another one here, maybe. We want to know how many moles and molecules are there in, we'll go 32.5 grams of C2H4. So some things from the periodic table that might be helpful. Carbon 1201, hydrogen 1.008. So we're looking for 2 answers. How many moles? And then how many molecules would that be? Take a few moments, see what you come up with. because ultimately I also want to get to molecules. So again, that's the key, that you do have to use Avogadro's number. Along the way, though, I do want to stop at moles, right, to visit for a little bit. And we are starting with grams to moles to molecules. And again, we want to think about sort of what ties those together. And that is going to be our molar mass from the periodic table, right? Our molar mass from there. And again, moles to really badly written molecules there. There go. Is going to be our Avogadro's number. So again, that is the pathway we want to go. We do need to calculate the molar mass here for this guy. So again, we would go to the periodic table and just add up all the parts. There are 2 carbons, each from the periodic table, 12.01 grams per mole. Again, coming from here, and that's for our carbons. There are 4 hydrogens, each at 1.008 grams per mole from the periodic table. And again, we're just going to add up all the parts here, and that would get us our molar mass of 28.05. Again, those are grams per mole. Again, we know we could use this as a conversion factor that way, or if we needed to, we could flip it around as moles per 28.05 grams. By the way, if you were asked what is the molar mass, that is the way you would present it, with the grams per mole is typically how you would present it as the answer. We also need our Avogadro's number, which means in this case, 1 mole of C2H4 would give us our Avogadro's worth of molecules in this case, as this is not just an atom from the periodic table. So here we would use those molecules as the unit. Now we really have everything we need to do this calculation. We will start with what was given to us, which is 32.5 grams of C2H4. Once again, if it helps you, you could put it over 1, and that should point you in the right direction here, that I need to get rid of grams. Opposite location, grams on the bottom here will do that for me. And in this case, I'm actually going to get an answer because it was part of the question. So I will actually get our answer here. Grams will cancel, going to multiply and then divide. Not much to multiply up on top since it's basically times 1. We'll take 32.5 divided by 28.05. That is going to give us 1.16 moles of C2H4. I'm going to round here because we are looking for that as sort of an answer to the question in this particular case. First off, any questions on the first part there? That essentially took me from there to here, right? I'm sitting now at moles, and I now need to go the rest of the way. Once again, it's going to be Avogadro's number is what's going to allow me to do that. So I'll just pick it up from my boxed answer there. And again, if you're not sure, that is still up on top, right? So that is still up on top, the moles. And that is going to help me decide for my second, what should go on the bottom, moles or molecules? Moles, so they cancel. So moles of C2H4 should go on the bottom. Avogadro's number here should go up on top. And again, these would be molecules. Again, different than moles. Yeah, so different things. In this case, we're still multiplying what's on top, dividing by what's on the bottom. And in this case, we'll take our answer, and I'm actually going to take the non-rounded number, and I'm going to times it by 6.022, making sure to use my exponent button. And we will end up with, looks like 6.98 times 10 to the 23. These would be molecules of C2H4. Any questions on any of those steps? So again, you want to keep in mind not to use Avogadro's number in the wrong situation. You got to have molecules or atoms given to you, or you're looking for it. And again, always grams to moles, moles to grams, periodic table, molar mass is what you want. Any questions on any of that?